Yesterday. So just now we have done with pure capacitor, pure resistor, pure inductor and pure capacitor, and this is what I have done. Differences between resistor, inductor and capacitor. This is how we differentiate. For pure resistor, again I am repeating. For pure resistor, current and voltage are in phase. Phase difference is 0, and then it has a power dissipations. Alright, and then in case of pure inductor, current is behind voltage by pi by 2, and average power is 0. So this is the Phasor representations. And in case of pure capacitor, current is ahead of voltage. All right, voltage is behind, current is ahead, voltage is ahead. In case of this case, voltage is behind, current is ahead. So this is what we have. All right. So now having this, right, we will try to do the voltage applied to a series LCR circuit. So this is very important. All right. So now I would like to do this. So I'm going to arrange all the three components, that is resistor, capacitor and inductor in a series combinations, and I'm going to apply a voltage. This is the source voltage. This is the source voltage, right? This is the source voltage. The voltage I'm going to apply voltage. This is the voltage we are going to apply, Vm sine omega t. This is the voltage across the source. Voltage across the source, right? Or voltage applied, right? That is what we call as voltage applied. And then we will be having VR is the voltage across the resistors, and VL is the voltage across inductor, and VC is the voltage across capacitor, right? So therefore, using the Kirchhoff's rules, what we can say is that VR plus VL plus VC is equal to applied voltage. So this is what we have. And then again what I can write is, this is instantaneous current plus this is L di by dt. This is voltage across resistor, voltage across inductor, and the voltage across capacitors. This is equal to V. This is using the Kirchhoff's rule, right? And Q is instantaneous charge, I is instantaneous currents, and this is V is instantaneous voltage, right? V is instantaneous voltage, right? This is voltage, right? So this is what we have, right? So now what we are trying to understand is, using a Phasor diagram method, we have a two way of handling this problem, right? One is analytical method, that is solving this equation and then get the answer solutions, and other method or solution is use the Phasor diagram method and to find. And what exactly we are going to find is what is instantaneous current, right? And what is the phase difference between a current and a voltage? What is the phase difference between a current and a voltage? And what is maximum current? What is maximum current? So these things are what we are going to find out, right? So what is instantaneous current? We are going to find out. And what is the phase difference between a current and a voltage? And then we would like to understand what is the total impedance, right? Total resistance, that is total impedance. This is total impedance. So this is what we are going to find out. And look at here, what you should understand is that the current, right? This is the voltage we are going to apply, the source, and current along resistors, inductors, and capacitor will be having a same current, you will be having a same currents, alright, with the same phase and with the same amplitude. So current is same for all the three components, right? Current across resistor and current across inductor, current along a resistor, current along inductor, current along a capacitors are same, right? With the same phase, same amplitude, right? And this is the voltage supply from a source. Source voltage and the current, this is what we are going to do, right? So, alright, so this is what we have, and this diagram is little interesting. So we say that this is resistor, this is inductor, and this is capacitor, right? Voltage across resistor, voltage across inductor, voltage across capacitors, right? Voltage across resistor, voltage across inductor, voltage across capacitors. Alright, and now this is the phasor voltage across resistor, and this is the phasor voltage across the capacitor, this is the phasor voltage across resistor, that's it. And now look at here, the current, I told you, the current all along resistor, inductor and capacitor the same, alright, same phase, same amplitude, right? So therefore in case of resistors, current is along a voltage. Current, the voltage of a resistor, voltage across the resistors and the current in a resistors are along a same. They are in phase. Phase difference is 0, right? Now in case of inductors, alright, the current along inductor is behind voltage by pi by 2. So this is what I say, minus pi by 2. Minus pi by 2 tells that current is behind. Current in a voltage, current in an inductor is behind a voltage across the inductor by pi by 2. Now in this case, current in the capacitors is ahead of voltage across the capacitor by pi by 2. So this is what we say that this is nice diagram, right? You can get entire concept from this diagram. So this is what we have. Alright, so to solve this problem, what I'm going to do is, alright, first I shall take input voltage. So this is the voltage applied across, this is the voltage. This is voltage across the source, this is voltage across the source. And now what I say is that I'm going to put this is the phasor. I is a phasor currents along resistor, inductor and capacitors. And I say that this is what we have, right? And then we have this is VR, this is all are vector, right? Current, phasor means phasor voltage, phasor current, that means the phasor current, right? This is inductor, this is capacitor, and this is voltage, phasor voltage, voltage across resistor, inductor, capacitor, and source respectively. This is what we have. And now what I would like to do is having this for resistor, V is along I, right? For resistors, VR is parallel, right? Or along VR is parallel or along I. This is for paired resistors. So therefore phase difference is 0. Therefore phase difference is 0. This is exactly written in a diagram, right? Now for inductor, VL is ahead, pi by 2 ahead of current, pi by 2 ahead of currents. So therefore this is what we have, right? Phi is going to be, right, pi by 2. So let me this is the diagram, right? This is the diagram. Let me write here also, right? This is the diagram. This is the diagram, right? So V and then VL, then I, and this is pi by 2. This diagram is this, right? Now, for inductor, for capacitor, VC is pi by 2 behind, VC is behind pi by 2 behind voltage, behind current by pi by 2, right? It's behind current by pi by 2. So this is what we have. So this is behind, right? So this is behind, right? So current is leading, right? So the diagram I would like to write is this is VC, this is I, we have. So this is pi by 2. This is what we have, right? Now what I would like to do is I would like to combine all, right? So before that we see the length of this vector, right? Phasor represents the amplitude. The length of Phasor vectors, right? I would like to write here the length of Phasor vectors. Length of Phasor vectors represent amplitude. Therefore, or maximum peak or maximums. Therefore, look at here, VRN, right? This is what we call as VRN. All right. So the length of Phasor vectors, that is amplitude of resistors, that is VRN is equal to IN. This is the length of or the amplitude of voltage across resistor, right? And this is the amplitude of voltage across inductor, right? And this is the amplitude of voltage across capacitor. And then let me write here for your understanding, right? All right. This is what we have. All right. And then I've used the Kirchhoff's rules. Just now we have done it. VR plus VL plus VC equal to V, or the vector sum of, I'm going to rub this. or I say the phasor voltage across resistor. Let me write. This is a vector. This all are vectors. So just to specify this, I would like to write here. Inductor plus capacitor equal to V. This is how we represent. This is how we represent. All right. Now look at here. We say that this VC, VL, vector VL and VC are along the same line. But in opposite directions. And one more, I say VR is along current phasor. VR is along a current phasor. Alright. VR is along a current phasor. So let me write here. VR is along a current phasor, right? So VR is along a current phasor. And now look at here. So therefore the magnitude of, I would like that magnitude of V L plus VC is equal to V LN minus VCN, right? This is what we have, right? So now let me draw a diagram, right? So I'll be having this. I'll show you this diagram in just a few minutes. This is how I represent, right? VR is along I, right? This is VR. I and let me say that current, right? Let's say I'm sorry, right? I is equal to Im sine omega t plus phi. This is very important, right? I have to write it once before, right? Anyway, right? This is what we have. All right. And we would like to find out what is phi and what is I and what is Im. I told you before, right? What to find out? I, Im and phi is a phase difference, right? Phi is a phase difference between I and V. Alright. So therefore this is what I have. This is equal to omega t plus phi. And then now look at here. What about current, right? What about in case of inductor, right? In case of inductor, voltage is ahead of current. Voltage is ahead of current. This is inductor, right? Voltage is ahead of current, right? This is for inductors. Voltage is ahead of current by pi by 2, right? This is by pi by 2. What about in case of capacitor? Current is ahead of voltage. This is what we have. So that is why I say that VL and VC are along the same line, but in the opposite direction. This goes in this direction, that goes in the opposite direction. And I say that VR is along I, VR is along R. This is what we have, right? This is what we have. And then magnitude of this is going to be this, alright? Or I say this is going to be opposite, right? So since this is longer, I would like to write here this is C, doesn't make any difference, right? Whichever you write, alright? CM and N. This is the magnitude. And now I would like to see what is that value? Alright, so magnitude of VC plus VL is equal to VCM minus VLM, which is equal to IM XC minus IM XL. This is right. Okay, now I just say this is going to be just sum up, and then what we are going to get is the second that I'm going to write is this is equal to VC plus VL, and this is equal to VROI omega t plus phi. Now what I'm going to do is I'm going to solve this. Now looking at this, we say that I'm going to use this using a vector diagrams, parallelogram law of vector addition, right? Now using this, I would say that this is going to be something like this. Alright, this is alright, and this would be V, right? So vector along this. So I say that vector V, I represent this. Vector V is equal to R, something like this. Alright. And what is vector RC plus RL plus, and VR gives you V. So this become the magnitude of V become a hypotenuse, magnitude of this become hypotenuse. So this become hypotenuse. This become hypotenuse, and magnitude of these two, right? The magnitude of these two become two sides, right? The length of two sides, right? Right? Two sides, right? These are the two sides. So therefore, what I'm going to do is now, and now using Pythagorean theorems, I say the magnitude of this Vm. Using Pythagorean theorems, Vm, all right, square is equal to Rn square plus, and then Cm plus I'm sorry to say the minus this magnitude, I write this Vlm V, right, whole square. This is the magnitude. This is the magnitude. Alright. So now substituting, alright, V is equal to Im R plus Imxc, this is C, right, minus Imxl whole square. Now let me solve these equations. Let me solve these equations. Let me solve these equations. So Vm square is equal to R is common, then R square plus Xc minus XL whole square, and then I just squaring both sides. Vm is equal to Im root of R square plus Xc minus XL whole square. This is L, looks like C. And now I got it. I is equal to Vm, Im is equal to Vm divided by root of R square plus Xc minus XL whole square. This is the point. And now this represents, so this is equivalent to Vm divided by Z. Alright, where Z I call is a total impedance. Total impedance, which is equal to root of R square plus XC minus XL whole square. Z. And now we would like to find out what is phi. This is phi. Now we would like to find out what is phi, right? So phi, I can get you phi. Phi is equal to, look at here, this become a perpendicular, right? This become a perpendicular, this become a base, right? And look at here, this is phi, right? And this is omega t. This is omega t plus phi, and this is omega t. And what is this? This value, this is equal to phi. Alright. If this is phi, then I can say that tan phi, which is equal to what is perpendicular? Perpendicular is VC minus VL divided by XL VR. So which I can rewrite this as IMXC minus IMXL divided by IMR, and IM cancel out. Finally we get XC minus XL divided by R, and this is what we call as impedance diagram, right? So therefore we got phi. Value of phi is given by XC minus XL divided by R. This is the value of phi. This is the value of phi. This is the value of phi. Alright, this is the value of phi. Now once we found the value of phi, now we would have to get this, right? I is equal to Im. How much is Im? Im is equal to Vm divided by Z. What is the Z? Z is impedance. And again, I can rewrite this, and Z can be represented by this, right? So I have one more diagram. Alright, this I can show you. I can have these diagrams. This is going to be Z, this is going to be R, this is going to be XC minus XL, and this angle is going to be phi. Alright, so therefore I just say phi can be written as tan inverse of XC minus XL divided by R. This diagram is called impedance diagram. This diagram is called impedance. So now we sort out, or we could get all the information, right? So we can get it Im and omega, the phi is equal to, this is how we got it, right? So this is what I have done. And let me do a small recapitulation for this with the textbook diagram. So this is the phasor diagram. Just now I explained. This is phasor voltage, phasor current across a resistor. This is the voltage across resistor. This is voltage across capacitor. Why? Because this is voltage is behind current by pi by 2 in case of capacitor. Voltage is ahead of current by pi by 2 in case of inductor. This is one case. And then now solving this phasor diagram method, this is what I got. Alright. So this is what we have. This is vectorially I'm saying, right? Magnitude has to be minus, right? So this is what we got it. And I say that, and this is the perpendicular component, this is the base, and this is the hypotenuse, and phi is the phase difference between a voltage and current. This is the current and this is the voltage. Alright, so this is what we got it. And now next, this is the overall, right? This is the overall, right? Alright. Yeah. So this is again one more diagram is there, right? This is impedance diagram, right? Impedance diagram. This is what I have written here, right? Z, R, and O, right? This is maybe in exam if you ask something about impedance diagrams, then this is the impedance diagram which I have written here, right? Again, this is the better diagram with some color, right? So this is VC, this is VL. They are along a straight line but opposite. So therefore, the magnitude would be the minus, right? This is equal to VC plus VL. You may be surprised why pi plus. This is a vectorial made out, so magnitude will get minus. Okay. And now this is, I will tell you, this is omega t plus phi. Initially we consider, right? Initially we consider, and this is the resultant vector V, that is voltage across the source. So therefore voltage across source is omega t, right? And what is the phase difference? What is the phase difference between voltage and current? Phase between voltage and current is phi. Now how much is phi? This is the phi. Alright, now having these diagrams, alright, I would like to do a small two cases, right? That is, first case study is if XC is more than XL. If XC is more than XL, then phi is positive. And we call it as a predominantly capacitives. That means the circuit is dominated by capacitors. So therefore we call it as a predominantly capacitive. And in this case, current is ahead of, right? Current leads, right? Or ahead of voltage by phi. So current is leading the voltage. Right? So this is what we have. And second case, if I say if omega XC is less than XL, if XC is less than XL, this is a positive, right? This is a positive. Then phi is negative. I'll show you this diagram. This is the diagrams. Alright. This is negative. Alright, this is negative. Why? Because this is going to be omega t plus phi, alright, and this is going to be omega t, and therefore this is going to be phi, which is minus, right? Which is minus. Alright. So this phi has to be minus. This has to be minus, so therefore phi is negative. Okay, and here in this case, voltage is ahead of alright, is I is behind, right? I is behind V by phi. O, voltage is ahead of current. O, voltage is ahead of current by phi. And this is what we call as, this circuit is what we call as predominantly inductive. This is what we call as predominantly inductive. Alright. So this is what we have, right? Now I discussed all the two cases, right? Two cases. Alright, this is predominantly inductives, other one is predominantly capacitives. This is the diagram, right? You can, if you like, you can take this diagram also. I will rub. This is VL minus, now VL minus VC. VL is more than VC, therefore you got this diagram. This is minus omega t minus, right? Right. So therefore this is what we have. Okay, now Now next, I would like to do a resonance, right? Next, I would like to do is a resonance. Now the same. Now look at here. Now when you study LCR circuit, when you study LCR circuit, we would say that current, right? IN is equal to Vn divided by root of R square plus Xc minus Xn whole square, and we say that Xc is equal to 1 by omega c, Xn is equal to 1 by omega L. This is what we have. This is for amplitude of current, right? Now, when you study this very carefully, both capacitive reactance and inductive reactance depend on omega, right? In opposite way. That means, in case of capacitors, omega increases, capacitive reactance decreases. All right? I said it increases, then this is going to decrease. Now, in case of this, omega decreases, then XL, and this is what increases XL. This is what we have. Because of these relations, we say that at particular frequencies, at particular frequency, let's say that frequency is equal to, at particular frequency is equal to omega naught, then Xc is equal to XL. Xc is equal to XL at particular frequency, and we call this frequency as a resonant frequency. We call this frequency as resonant frequency. That we call this frequency as resonant frequency. At frequency omega is equal to omega naught, Xc is equal to XL, right? So therefore now Xc is equal to 1 by omega naught C, and XL is equal to omega naught L. Alright, therefore 1 by omega naught C equal to omega naught L, omega naught square is equal to 1 by LC, omega naught is equal to 1 by root of LC. So that means if omega is equal to omega naught, and you would ask what is the value of omega naught, the value of omega naught is this, 1 by root of LC, and the value of omega is determined by the property of inductors and capacitors. Alright, so the value of omega, that is the resonance frequency, is the characteristic of L and C, and this is equal to 1 by root of LC. Now if I fix the omega equal to omega naught, then Xc is equal to XL, then Xc is equal to XL, and then what we get is, then finally what we get is, Im is equal to Im max, that is the maximum amplitude of current. This is what we call as maximum amplitude of current. This is what we call as maximum amplitude of current. This is what we call as maximum amplitude. This is going to be a one particular maximum amplitude of current, right? This is one particular maximum amplitude of current. Let's say R1, and this is another maximum amplitude of current, R2. So this is what we have. So at this particular frequency, that is omega naught, at resonant frequency, current in a LCR circuit would be a maximum, so you would get a maximum signal, right? So this is what we call as resonance, the minimum resistance or impedance and maximum current, right? So this is the peak. You get a peak, and now the height of peak, right? The height of peak of LCR circuit is determined by resistance. If resistance is high, peak is low. If resistance is low, peak is very high. And one more, the physical application this is whenever we talk about in case of radio and all, if you could fix your frequency at a particular bandwidth or particular frequency resonance, then you could get signals, right? That particular signal would be a maximum, so you could get it, right? So this is, and the detail you will study later, right? So this is what we are resonance, and detail we will study next class, right? So this is all about resonant frequency. Thank you. So next class we will discuss the remaining part, that is the sharpness of resonance. In that case we will study little detail about resonance. Thank you.